Welcome back to the Learning Studio. You're watching our mathematics series in the section on data, algorithms, and computation, where we explore the mathematics that powers AI, algorithms, and modern computing. If you're joining for the first time, don't forget to follow us by clicking the link below. And remember, the full playlist is in the description, so you can enjoy every episode in order. Today, our topic is nonlinear optimization, the mathematics that drives deep learning, reinforcement learning, and the search for solutions in complex, multidimensional spaces. Think about training a deep neural network. It starts with random guesses for millions, sometimes billions, of parameters. The network doesn't know anything at first, but through trial, error, and adjustment, it slowly learns to recognize images, translate languages, or even master video games. What guides this learning process? The answer is optimization, specifically nonlinear optimization. Core concepts explained simply. Here are the essentials. Optimization basics. In optimization, we want to minimize or maximize a function, like minimizing the error of a neural network. Linear versus nonlinear. Linear problems are straightforward, but most real-world problems, especially in AI, are nonlinear, meaning the landscape of solutions is curved, irregular, and often filled with local minima. Gradient descent and beyond. Deep learning uses gradient-based optimization to adjust parameters step by step. But advanced methods, like stochastic gradient descent, momentum, and adaptive algorithms, Adam RMS prop, make optimization practical at scale. Reinforcement learning. Here, optimization isn't just about fitting data. It's about maximizing rewards in uncertain environments, requiring exploration, policy optimization, and handling stochastic outcomes. Challenges. Nonlinear optimization faces rugged landscapes, saddle points, and exploding or vanishing gradients. This makes the theory and practice of optimization critical for modern AI. Why it matters in AI, computing, and technology. Nonlinear optimization is the engine that powers intelligence. In deep learning, it's what allows models to learn from massive datasets and improve performance over time. In reinforcement learning, optimization guides agents to discover strategies in robotics, gaming, and autonomous systems. In operations research, nonlinear optimization solves complex real-world problems like supply chains, energy grids, and financial modeling. In science and engineering, it helps find best-fit solutions in nonlinear systems where exact answers are impossible. It's the practical bridge between abstract mathematics and working AI systems. So, nonlinear optimization is the mathematics of searching, adjusting, and improving, the process that transforms raw models into intelligent systems. Without it, deep learning and reinforcement learning simply wouldn't work. In our next episode, we'll take a step into differential geometry, exploring manifolds, general relativity, and their surprising role in modern geometric machine learning. Don't forget to follow us by clicking the link below, and check out the full playlist in the description. With each episode, we're uncovering the mathematical foundations of intelligence, piece by piece, layer by layer.